this lesson, we're going to go over the pipe conveyor feature embedded in Belt Analyst to evaluate and design pipe conveyors. We're going to start off by assuming that anyone watching this video is already familiar with Belt Analyst as far as designing a conventional conveyor, as you see on the screen right here, because most of the features that are used in Pipe Analyst are the same as a conventional conveyor, such as pulley designs, etc., etc. So as we go through the tabs here, the material properties tab is exactly the same. The length and lift, flight inputs is exactly the same. The idler spacing, the percent loaded, skirting, load area, cleaners, plows, how you move drives around, move the take up around is exactly the same as a conventional conveyor. So one of the nice things about having pipe conveyor embedded in with this conventional conveyor is that you can put your profile in, your links and lifts and where you're going, and very quickly compare a pipe conveyor option versus a conventional conveyor option. So when you're ready to look at the conventional or a pipe conveyor option, you go to the options menu, belt type, and you see standard belt, which is conventional, and pipe conveyor. So when we click on pipe, you see the program goes through a series of iterations, changes the calculation method, and you can see it visually on the screen. We're now looking at a pipe conveyor. The belt width on the main screen here is changed to pipe diameter, and we can easily change the pipe diameter if we'd like to, and input whatever diameter we'd like. If we happen to select a pipe diameter speed combination that doesn't allow us enough room to carry that material, the program will tell us that and change the, in this case, change the tonnage, the capacity throughput. I'll take that back for now. The belt width has been moved to the belt tab, and you can see there this in the auto mode it's picked a 1500 millimeter wide belt for this pipe diameter. Just like it with the rest of our products, in auto mode a lot of things are selected automatically, and in user mode you can now adjust the belt width to whatever you'd like it to be if you'd like to use something different. The rating of the belt, cover gauges, weight, modulus, all these things the same as a conventional conveyor. You'll see up here in the calculation methods that a lot of these methods have gone away. Now we have a pipe conveyor calculation method and what we call a modified DIN. So in the pipe conveyor calculation method, it is a proprietary method to overland conveyor, as there are no standard methods published in any of the best practices or industry standards around the world. So it is a modified calculation method that we have developed and documented over many years of doing pipe conveyor designs. If you'd like to input your own, and you can see down here in the bottom right hand corner the resulting friction coefficient that would be equivalent to the DIN F coefficient, in this case 0.0324. If you'd like to put in your own F factor, you can change that method and put in your own value here, and the program will use that value. There's a small adjustment that's been made here for the width and for the speed and temperature. There's a slight speed adjustment that's been made there. If you'd like to have this thing use exactly the 0.05 value, put it down here at the bottom, and it should use that value, and you see it come up down here at the bottom in the friction coefficient calculation. So you can certainly put in your own coefficients if you'd like to. If you'd like our program to calculate that for you, just click the pipe calculation method. If you'd like to see some of the friction coefficients that's actually computed in here, it is a methodology is a KX, KY, so the friction coefficient is divided into two components. and this is similar to the SEMA standard method, which is referenced in the conventional conveyors. KX represents the idler rolls, and KY represents the bending and the pipe forming and the sag and all the other rubber indentation, all the other factors involved. And you'll see here that the KY is tension dependent, so those values do change as the tension changes. The only real thing that's important to keep in mind here, because the power calculations are all, of course, done here for you, wrap angles, slip factors, take-up requirements, all very much the same as a conventional conveyor. Pulley calculations, same as a conventional conveyor. The idler L10 life calculations, very much the same as a conventional conveyor. The only big difference, and this is an important one to highlight, is all the curves. Of course, in this particular profile, I've just got a straight 1.2 kilometer flight with no lift, and I have no curves defined vertically. The only thing we can define in Belt Analyst is the vertical curves. Obviously, we don't have the horizontal plan type view, but we can add the curves, and we need to add the curves to pipe conveyor calculations manually. So even if we do insert some curves into this analysis, the curves are not automatically accounted for in the calculations. We have to manually account for those curves, all curves, both horizontal and vertical. So the curves you see here, it starts off with a blank screen, and this is important for us to put all the curves in, because in Pipe Analyst, in pipe conveyor calculations, every time this pipe goes around the curve, there is losses, there is drag in the system, because we are bending a pipe. Our methodology here is bending moments of a pipe. Therefore, the higher the modulus of the belt, the more drag there is in bending that pipe, and the more power required. So just to give you an idea here, if I have a vertical curve at this location, if I give it a label and define that as a vertical curve, and then input the vertical curve radius, you see that you have the option now of defining that as either a concave or a convex curve, whichever it is. You get an equal and opposite curve on the return side whenever the geometry is in auto mode. So in this case, we put the geometry in the carry side, and as you know from the conventional system, if we're in auto return, we get equal and opposite return flights. So as long as we're in auto return, you'll see it automatically selects the equal and opposite curve on the return side. If you're not in auto mode, you'll have to define the curve radiuses in both the carry and the return side. I'd like you to look down here at the power requirements quickly, because every time you'll see here, every time I input a radius, that the power requirements do change, and in this case it actually went up to a higher motor, to the next size motor, and you can see the friction coefficient went up, the total friction coefficient, that is, and this is because there is power in each one of these curves that we put in, power requirements. You can see there the 150 did stay yellow versus the blue. That's because that is we do have a rule of thumb as to what the minimum radiuses need to be based on pipe diameter, and if you don't follow that rule, these numbers will stay yellow to indicate that the rule is broken. We're not making any conclusions as to what these radiuses need to be. That's very much a function of you as a designer and the belt manufacturer. So keep in mind that we're not making any recommendations on radius here. I will import here a horizontal curve. You can input horizontal curves and vertical curves in this case. And again, you see the power has gone up, and I'm going to go ahead and extend this horizontal curve over 2 sections. If the curves are back to back, that means the curve does extend over more than one flight, and in this case, horizontal curve 1 in this case would extend over 2 flight sections. It's considered one curve in the program with a 200 meter radius, and you can see that highlighted by the colors here is how it's differentiating between where the curves are. So this is very important in the program here, that all the curves are identified and located, because they are part of the power calculations. And just to give you an idea of how the belt construction influences that, I'm just going to come back here and say change the belt construction. I'm not going to, actually I'll change it up here. I'll pick a stiffer belt, a belt with a higher modulus, and you can see that the power requirements went up, because the stiffer the belt, the harder it is to bend it in that pipe, and that requires power. So the important things to keep in mind here is the belt width is moved over here to the belt tab, and all the vertical and horizontal curves need to be input independently of the profile of the conveyor. So make sure that's done, and then the power requirements and belt tensions and pulley diameters and idlers and everything else should be just the same as a conventional conveyor.